Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, it's my great pleasure to introduce Marin Hill. Marin is in the University of Texas, Austin. He's very influential in the Satis community. He's the editor of the Handbook of Satisfiability, the author of a very efficient Satis solver called March. He's also was the organizer of the last Satis competition, and today he's going to tell us a little bit about his latest work. Thank you.
Thanks for the introduction. So my talk today, and so if anything is not clear, ask questions. My talk today is about unsatisfiability proofs, and so I kind of before I started working on this, there was either it was easy to make proofs, but they were very inefficient to check, or they were efficient to check, but it was hard to create them. And I kind of present work here that's bridged the gap between both favorable properties. And this is work together with Warren Hunt and Nathan at UT Austin. So, a short outline. So I've do some motivation and the contributions, and talk about the different kind of proof styles that is resolution and clausal proofs. I go into detail about it. The big disadvantage of clausal proofs is that current methods were very inefficient to check them, and I will explain here techniques how to check them efficiently. I also will talk about expressive proofs, that all the techniques that are used in the state-of-the-art solvers, how can we express them? And in the end, I will, just before conclusions, I will mention kind of the future direction that we actually want to have a mechanically verified checker that does all the things I talk about. So, satisfiability, especially with, you know, here at Microsoft, they're used in many tools, especially C3. They're used to find counterexamples. And then if you have a SAT benchmark, you have a solution for it that are used for many equivalence checking problems for miters, but are also, you have more bigger answers which kind of say they're used for diagnosis, that you ask what is a small explanation for why it's unsatisfiable. And what we are interested in also in Austin is we want to have a small proof for benchmarks which are unsatisfiable, such that we can check it with a valid mechanically verified checker. So we can trust the output of the SAT solver. Although there are lots of positive news and they're used in so many applications, there is also negative news. And one of them is that there are bugs in SAT solvers, and not only on SAT solvers, also SMT solvers, and especially QBF solvers. Even winners of the competition have bugs. So last week I was at FMCAT, there was the hardware model checking competition, and there was 7 rounds of bug fixing allowed to, that solvers were kind of not buggy on version.
You know the solver that does not have bugs?
No, yeah, so the problem is you cannot really trust the solver, but you want, so that the whole idea is we want to trust the output of the solver, so that we cannot be sure that the solver always gives correct results, but you want to emit something that you can say, okay, for this result I can trust because of this and this and this. So then you don't have to trust the solver, you only have to trust the result for the specific things you are interested in. Does it make sense?
Well, it seems like if you can always trust the output, then in some sense you could define that as free of bugs that you care about.
Yeah, no, but so you will check the output for each instance. So you have a problem. You have so I will show you in a slide soon. But you have a problem. You solve it by a solver. Then it gives you some kind of proof, and then you have a checker, and that has the same problem and the proof, and then you check whether the proof is correct. So you don't have to trust the solver only if the proof is incorrect. Yeah, then you don't know what it is. So the solver might have given a bug. But if the proof is correct, then you have a proof for the problem. So the answer for the problem is you know. Does it make sense?
Wait, okay, so you're going to talk about how the checker is bugged for you.
Yeah. So that's the final step. But I think that's slide 35. It's about that you have a formal proof for the checker, and therefore you have in the end a formal proof for the proofs emitted, certified proofs. But yeah, there are several steps in between. And so the main contribution for this work, what I will talk about, is a tool that can efficiently validate results. Oh, so yeah, I didn't talk about this yet. That for many of or actually all existing tools that provide these two things, so unsatisfiable cores or small proofs, they use a lot of memory. And with a lot of memory is that these tools for benchmarks used in the competition, if you turn on this emission, memory consumption increases up to a factor 100. So, and due to this memory increase, solvers slow down and eventually go out of memory in a relatively short time. So, and what we have, so the tool can efficiently check results of a given proof, but also can produce these results without requiring much memory. So that's what I will talk about. So I guess everybody here knows about the satisfiability problem, so I don't have to go too much into detail about that. But given a Boolean formula, is there an assignment that satisfies it? Throughout this presentation, clauses will be denoted by blue boxes, and there will be 3 Boolean variables, A, B, and C. And negative literals are denoted by negation. So the first clause is not B or C. It is easy to check whether an assignment satisfies this formula. For instance, the assignment not A and not B and C. We just scan over the formula to see if each clause has one element in the assignment there. I guess this is clear for everybody. Unsatisfiability is much harder, and this is done by checking clauses that will be added to the formula. And most of the techniques can be expressed using resolution steps. So resolution works as follows. So you have a pair of clauses such that they have a complementary literal, for instance, B and not B. And then what we can do with the resolution rule, we take the union of the clauses and remove the complementary pair. So resolution with not A and B, not A or B and not B or C gives us not A or C. And the same thing we can do with another. And the purple circles mean lemmas, which mean that are not original clauses, but that can be added by resolution steps. And so on the left there's a resolution derivation, but I will use this notation throughout the presentation, which means that we can construct lemma C using resolution, using these clauses, but we don't specify how.
I guess you do, because you want them when you can do it by units.
Yeah. So you can reconstruct it, but so this notation does not specify exactly how you do it. So this notation specifically specifies how the resolution steps are. So there's not an order in which the resolution. So you can give an order, but this, if you look at this, you don't know exactly how to do it. Of course, you can reconstruct it. You can reconstruct it in linear time, but it's just notation.
But arbitrary resolution proofs you can't reconstruct in linear time.
No, not arbitrary. No.
So there's some. If I recall correctly, you have a restriction, which is that the steps have to be reconstructed by unit propagation.
Exactly. That's also the restriction I will use. But I will come back to that later.
Maybe I'm anticipating too much, but it's just...
Yeah. No, yeah. So in this case, I just want to say that we don't specify it like throughout all the drawings will be like this and not like that. So, and this is what I just talked about earlier, the kind of the tool chain, although it will get a bit more complicated, but you have a Boolean formula, you give it to a SAT solver. If it's unsatisfiable, you also require that it to have some proof of unsatisfiability, and there can be several kinds of proofs. And the proof and the original formula are given to the checker. So you don't have to trust this. As soon as this is correct and this is correct, then and you trust this, or this is verified, then you're done. Is that clear? So I will also talk about redundant clauses a lot. Now, what is a redundant clause? If you add it to the formula, it remains equisatisfiable. So if it has the solutions, adding the clause, there will still be solutions. And also for removal, if it's unsat and you remove the clause, then it remains unsat. So it's a more general notion than a logical equivalence, and that's necessary for some of the properties I will discuss later. So it's just, if it has solutions and you add it, there still are solutions. It might be fewer solutions. And if you remove it, if it's unsatisfiable, then it's still unsatisfiable. But if it's satisfiable and you remove it, you might introduce solutions if you remove it. What is a proof trace? You have a formula and a proof. And so the formula, everything they can be of arbitrary order, but the proof, there is an ordered sequence, a sequence of lemmas. And how does it work? We have a formula and we do some checks that say that the formula with the clause from the proof is satisfiability equivalent with the original one, and then we add clauses until we add the last clause in the proof, and we call it a proof of refutation if the last clause in the proof is the empty clause, which is denoted by this symbol. So if that one is at the end, then the empty clause cannot be satisfied. So if the empty clause is redundant, satisfiability equivalent, then we know that the original formula is unsatisfiable. So there are kind of two kind of proofs, and also I'm not going into detail here yet, but in the next slide. One is resolution proofs, and the other are clausal proofs. And there are kind of four properties you kind of really like to have in a proof format. And what is the properties? You want a proof to be easy to admit, so that you do not need lots of changes to the SAT solver to obtain a proof. And for resolution, it is there can quite obstacles to implement it in the state-of-the-art SAT solvers. For clausal proofs, it's very easy. I will show that later. You want to have them compact, and compact is for competition results is kind of a few gigabytes, which is what clausal proofs can do, but resolution proofs can quickly grow to hundreds of gigabytes. You want things to be checked efficiently, and so the resolution proofs are big, but they can be checked efficiently. And clausal proofs are existing methods are expensive to check clausal proofs. So our contributions, so I will mostly focus on this is that by adding deletion information, which is a feature of the solvers, you can make checking much faster. And here I will present more techniques to really speed up the checking. So then we combine easy admission and compactness with efficient checking. And what you also kind of want is that you want to have things expressive, which means that you want to cover all existing techniques in SAT in a proof format. So resolution and clausal proofs have the same kind of expressivity, and they can cover lots of techniques. However, there are several techniques that are not covered, and at Kate I presented this year another format which is very expressive, and this is kind of this now the state of the art. Although so in the future I want to combine everything so that I have it all. So I have also the expressivity here, but it's kind of more tricky to get, and the efficiency and the expressivity.
So the Kate proofs, are they are for extended resolution?
Yeah, they cover extended resolution.
And so what about QBF proofs?
Yeah, I'm now talking about SAT solvers. I can.
So there are certain extensions of resolution, and in QBF there's this Q resolution.
Yeah.
Does that fit within these frameworks, or would that be an extension?
So I think it all fits in, but so these red proofs is I think can also be used for QBFs, but the procedure of checking it becomes more complicated because you have to also take into account the universal reduction, and you have to take into account the order of the quantifiers. So it's the check becomes much more complicated. But I'm just working out whether everything works and that you can do it. But I think for QBF it would be also a very nice way of having certificates, because if you enumerate all the solutions, it's very expensive, and having a clausal proof would be much more compact. But yeah, so it's kind of this red proofs is resolution and unit propagation combined, and then you also have to take into account this quantifiers and universal reduction, because that's also a well-known technique used in the QBF solvers. Yeah, but you want me to go? Does it answer your question enough?
I think so. I mean, I haven't read the Kate paper, so I was just, but I believe it was about extended resolution.
Yeah.
And then QBF would be an extension, but you say it somehow fits in.
It somehow fits in, yeah. Because I just submitted a paper with about these procedures for clause elimination and clause addition, which kind of describes how things should be changed in order to let everything work for QBF.
Okay, so you're already.
But it was kind of more in how, for instance, it's used in Blocker. You know, that's the main preprocessing tool now for QBFs, and they use also these kind of these procedures. But it's kind of explain how it works and that they are sound, and I still have to kind of work out how it's actually working all for proofs, and how to make a proof checker for QBF, because it's much more complicated.
Did you consider instantiation-based proofs, like I could?
What exactly do you mean? What kind of format do you?
So they have proof for EPR. So in principle, you get a grounding plus a resolution.
Yeah. No, so ideally, I would like to have this kind of as universal kind of proof construction as possible. But I think the way is to go from SAT maybe to QBF and to go up instead of going down. But yeah, I think first solve the QBF version before kind of handling even the more complicated class of. Yeah, I'm not aware of all the techniques used in all these kind of solvers, like how this is all covered by the. So, discussion about resolution versus clausal proofs. So what is so I will talk about the resolution graph. The resolution graph is on the bottom. It has all the clauses, and it has a sequence of clauses, and the sequence is based on when the solver learned the clause. And it has incoming args of the clauses that are required, clauses or lemmas that are required to prove it resolution, and it's a refutation if the top clause is the empty clause. And a resolution proof is just a simple description of the graph. It has, for each line, it has an identifier for each of the clauses and lemmas, and additionally it has describes all the incoming args. So the size of a resolution proof is the number of vertices plus the number of args, which is big, because so here this is a small proof, but typically there are millions of clauses, and on average, which I will show on the next slide, there are on average 400 incoming args in a proof per lemma. So the size is pretty large. I will also use the word core, and core is all the lemmas or clauses. So core clauses are clauses that can reach the empty clause in the resolution graph, and core lemmas are lemmas that can reach the empty clause. So for this resolution graph, all the clauses are in the core, and not A is not in the core because you cannot reach the empty clause starting from A, not A. And so one of the main problems is that they are huge. The other one is that they're hard to admit, these proofs. To give you some details, so this is, so here is the number of clauses, and here are the number of literals. So this is the number of literals average in learned clauses, which is on average about 40. And here is the number of, on average, the number of incoming args for lemmas in the proofs. And what you can see is that there are many more incoming args than literals in the learned clauses. And so in order to have a much more compact proof, you actually only want to store the red instead of storing the green. And that's the idea of clausal proofs. You only store the literals in the clause and not store the incoming args. And so based on this data, you can see that resolution proofs kind of are say on average kind of a factor 10 larger. But if you look to the memory consumption, it can be up to a factor 100 larger. And that's because clausal proofs are immediately dumped to disk, and for efficiency things, resolution proofs are kept into memory, so you have these big things into memory. So the idea is only store the red things, dots, and not the green ones. And so to come to your point, how do you now reconstruct? So if you only have the literals in the clause, but you don't have the incoming args, how do we reconstruct the incoming args? It is done using unit propagation, and unit propagation is clauses unit if all its literals are falsified except for one, and then we can assign the remaining literal to true, and that we do that until fixed points. A simple example, so we have 5 clauses here. We have the simple assignment not C. Then there are 2 unit clauses, not B and A, and we just, for instance, take one clause to extend the assignment. We say, for instance, assign not B to true, which creates another unit clause not A. We now take another unit clause, for instance A, assign it to true, extend the assignment, and now we're done. There are no unit clauses anymore, but notice that there is one falsified clause, not A and B. And this procedure can be used to reconstruct the args. And it works as follows. We have a procedure called reverse unit propagation. So the main idea is that we assign all the literals in the lemma to false and apply unit propagation. If unit propagation causes one of the clauses, original existing clauses, to become false as well, then we can reconstruct the arcs with all the unit propagation steps. So, and if we assign not C to false, and then we have these two units which falsify this clause. And the reason why we can add lemma, we are now allowed to add lemmas, is that if this clause is falsified, then one of the antecedents is falsified. So the only way to satisfy this is, so if all these clauses are satisfied, this must be satisfied as well. So therefore, this is a reason why this clause is redundant. Yeah, is that clear? So now we have a clausal proof.
It doesn't change the set of satisfying assignments.
Exactly. This procedure not, but so the one that I use for Kate, which will be later on in the presentation, will change the set of satisfying assignments. But this is keeping a logical equivalent. RUP. Yeah. So this is a clausal proof. So we have here the order of the clauses that in the order they have learned, and we're going to check them. And we check them by the procedure I just explained. We assign all the literals to false, all the literals in the lemma to false, do unit propagation, and we check whether there is a falsified clause. In that case, we reconstructed the arc. So, and the same thing we do for not A. Again, unit propagation falsifies one of the other lemmas. We do the same for not C, or assigning C to false, which creates this. And in the end, we apply unit propagation of all the clauses in the proof, which should result in a falsified clause. So in this way, by applying unit propagation, we were able to reconstruct the arc without actually storing them. And as soon as you checked it, you just throw them away. Or you can store them to disk, but you don't have to keep anything in memory. But, so the big disadvantage of this technique is that the existing methods are expensive to validate it, to reconstruct the arcs. So, now 3 improvements, how to do it more efficiently. So the first one was already proposed in the original paper. So the procedure I just showed you was described in a paper by Eugene Goldberg in date 2003, so that's a decade old. And they also proposed to do the other way around. So start validating the empty clause and go backwards. And if you use conflict analysis after you find reconstructed the arcs, then you can mark the clauses that have got an arc, and you only have to check the ones that have been marked during the process. So the advantage is that you have to validate much fewer lemmas. The disadvantage is, why I kind of initially was a bit against it, is that it's much more complex, because you have this conflict analysis procedure, so kind of the checker becomes twice as large. But in the end, it's too much of a gain to really kind of ignore it. And so but although it's a decade old, there was no procedure. There's no fast checker of this procedure available. So this is the first kind of contribution we have, is that we have a fast open source implementation of this. But even with backward checking, it's a 10 to 20 times slower than actually solving the benchmark. So we have here, so the solving time is much lower than, much less than actually checking it. And what is the main reason why checking is much more expensive than solving is that, besides that solvers learn lots of clauses, they also aggressively delete clauses. And by aggressively deleting clauses, they use the unit propagation goes much faster. And as a consequence, yeah, that's what you actually want to have in the proofs as well. So you want not only to exploit the learned information, but you also want to exploit the deletion information. And this is done by introducing gray boxes. So gray means the clause is deleted. So for instance, after you learned not B as a lemma, and there is not B or C in the formula, you know that you can delete not B or C because it's subsumed. So each assignment satisfies this, that also satisfies this. And so in the FMCAT paper we showed that you can also combine this by ignoring certain clauses while going backwards. And also a nice thing is that you show that we can optimize the clause deletion information during checking, such that that the tool that we provide does not only heavily shrinks the formula of a proof, which can kind of frequently 90% reduction, but also optimizes the deletion information so that if you want to check it with a verified checker, it's much faster. And the third optimization is so-called core first unit propagation. What I kind of observed while checking proofs is that if you do this backwards checking, then only say 10 to 20% of the lemmas and clauses will actually be in the core of the final core. So doing all this unit propagation over those say 80 to 90% lemmas and clauses is completely useless because you will never use them. So you kind of really want to avoid doing unit propagation on them because it's very expensive. And the idea to do is to have unit propagation first only on clauses that are already in the core, and do that until fixed point. If there's no clauses to propagate on in the core, you stop, or you try to find if there's a single one which is not marked. You propagate that one, and then you see if there are now again core clauses that are units. Yeah.
So when you start with the empty clause, you don't know what the core is.
Yeah.
So in the first round, you might have to scan a lot, and then your procedure will say, "Oh, reuse whatever I scanned before, and then scan more."
Yeah. So so if you have the empty clause, which is always marked during the start, then you do unit propagation, and only step 3 will be done. Because there are no clauses in the core, so everything will. So it's more expensive to. So for the first step, it's not a very good procedure, because it's more expensive. Because you first constantly check, are there any core clauses which become unit, but since there are no core clauses.
Right, but then I was wondering, how do you make step 2 efficient in the bootstrapping phase? It seems that step 2 might have to examine the entire trail.
Yeah, so
you do that in say looking at by traversing the trail in reverse order, or do you take the given clauses as?
Yeah. So what I do is, I have 2 pointers. So as soon as a variable is propagated, I mark it as to examine, and I first go over. So there's lists of clauses in the core and which are not in the core, and then I first check the core, and then the other one is kind of as soon as this one is reached the end, that all the variables have been checked for the core clauses, then it starts doing over the same variables. It starts to check the unexamined clauses of the non-core clauses. So I
guess the question is, in the first case, 2 has no core clauses. So Nikolai's question was, what is the optimization?
So it's some kind of use list optimization. I mean, if you or watch lists optimization, if you watch clauses that are already in the core first, then
Yeah, so I have these two pointers. So this trail, so they contain all the variables that have been set to a certain value, so are assigned. And for each variable in the order they have been assigned, I check, are there any core clauses becoming unit at this point? And for instance, first for variable A, and then there are not core clauses, then I go to variable B and then C. And yeah, you kind of get what I'm or
Yeah, okay, thanks.
And,
yeah.
So what I observed that in some cases you can even get this kind of a factor 5 speed up because it really kind of ignores all the things that that all the clauses that you kind of really avoid seeing them at all, because doing this kind of having this first loop, checking only only clause in the core already gives you a conflict, so you never actually reach point 2. So for benchmark with most work, it's kind of you propagate, hit a conflict in step 1, and then you stop. And another nice feature of doing it like this is because you kind of really try to postpone pulling clauses and lemmas in the core, because you propagate first on all these, is that the actual cores, both for the core lemmas and the core clauses, this will be smaller. Because you kind of always, okay, I really want to avoid pulling things in, because as soon as you would randomly do unit propagation, then you easily pull clauses in which are not in the proof yet. So now I will explain the same proof again, but now with the 3 optimizations. So on the left we have now the same proof, but now so we have these 2 clause deletions inserted, and we will do the proof in backwards, and we do it with the core first unit propagation. So the first step would be we mark the empty clauses in the core, and all the clauses occurring that will be at some point deleted in the proof will be removed from consideration. So that's why they are now gone. The first step is now we're going to do backwards, so we check the unit propagation on the empty clause, and which, for example, uses these 4 clauses to find a conflict. And then all the clauses which are involved are marked. Next step is we continue using C, and we reuse as much as possible, which is the not A, and then we end up with adding A or C, pulling into the proof. So when you use clause deletion information, so actually when you do backwards, that if you find a deleted clause, then you bring it back. Now we check not A, and we bring those 2 clauses in the core. Now the deleted clause not B or C is brought back, and in the end we have not B, but not B is not marked, so we don't have to do any check, we can ignore it, and then we are done. And notice that so it is kind of the same proof we had with the for the other example, but what the other example had not B, C, and the empty clause in the core, and now we have not A, so the proofs can kind of really change. But also notice that in the other example we had all clauses in the core, but now not B or C is not in the core. And this is also what happens. So you really you do not only kind of check whether you can reconstruct the arcs, but by reconstructing the arcs you can actually have a smaller proof and a smaller core. And that's so it's not only that you have information that you might think, okay, if you do everything during solving and you do it afterwards, you lose information. Actually, it's better to do it afterwards because you can really exploit it by doing this alternative unit propagation and other things.
Why don't you delete C? I mean, when you're processing backwards, right? You check that you could add C, that's correct. But now you know that C was not used in the past, right? Why don't you delete it?
Yeah. So actually it is deleted.
Okay.
Yeah, so maybe, yeah. So actually, so as soon as you start with not A, everything above it is deleted. So maybe it's just to keep the picture there, but so you cannot use you're not allowed to use any clauses that occur higher in the proof to be used during unit propagation. So as soon as you go down, so if you check the clause or lemma, it's out. So you verify it and it's out. So yeah. Because you can only reconstruct lemmas if which are below in the proof. So I implemented getting this deletion and clausal proofs information into the glucose solver, which won the SAT 2012 challenge. And the nice thing is that you can have this deletion information, everything outputted to disk with, say, 2-3% overhead to the running cost, with only adding 40 lines of code and using all techniques which are used in glucose. So you have all the pre-processing, everything, and yeah, the lines are actually very simple. There's a closed database management part of in the solver, and the only thing what you do is, if there's a clause added to the database, you print it, and if a clause is deleted from the database, you say, I delete it, and that's it. You don't have to do any more kind of tricks. The only thing is why it's 40 and not 20 is because the procedures are slightly different for the pre-processing and for the solving. So if that would have been the same, you could have done it with 20 lines. And even, yeah. Which is, and then it's, okay. I check it also with PicoSat. PicoSat is the kind of the state-of-the-art solver for resolution proofs. This is the fastest solver which has all techniques for resolution proof enabled. And if you run them both with proof logging, so PicoSat with resolution proof logging and glucose with derep logging, then what you can see, this is on the 2009 benchmarks from the SAT competition, that glucose, this is a so-called cactus plot, and which means that all the benchmarks for each line are sorted based on the y-axis, which is the time in a log scale. And so what you see is that PicoSat is much slower, and one of the major impacts here is that memory consumption increases a lot because of enabling the resolution proofs. And glucose memory output is exactly the same, because the only thing what you do is you dump a clause to disk when you learn it or when you remove it, but there's no additional memory consumption here. And the third line is the tool I implemented to check the derep proofs, which does the checking, which also computes the smaller cores and the smaller proofs. And this is the time to check the proof. So this does not include the solving time. So this is kind of what you see. It's a kind of similar, the cost of checking the proofs and solving the proof, and solving and generating the proofs.
It's 100 times faster, but on the first 100 benchmarks. And then you say that it solves twice as many? So
for kind of a given time, yeah, so yeah, you read the plot. So if you take a line for a given time, glucose is almost twice as fast. So that is kind of what I yeah. But as you can see, the running times for PicoSat are way higher, and so up to the point where so for 900 seconds, lots of these benchmarks. I think a third of the instances cannot be solved more than a third because of the memory consumption.
Trim is the checking, which is 10 times slower.
Yeah. So for here, there are a few exceptions, but for most of the benchmarks, say up till here, it's really close.
Can you explain why it has this jump? What's the bottleneck? Why it becomes suddenly 10 times lower?
Yeah, the bottleneck, I think so. I looked into it because what you kind of see, and one of the solutions is that for most benchmarks, this core first is really helpful, but for other benchmarks, it's really both the loops constantly interact with each other, which makes things much more expensive. And I think most of these benchmarks here, they are enormous, and they're only solved with preprocessing. And preprocessing, that everything is already resolution, and somehow the solver with unit propagation can really. It might be that there are 1 million variables and that it does unit propagation on 100,000 to check that only there are 3 have to be assigned to get really the conflict. So so the most important exceptions are benchmarks that can be solved with almost only preprocessing, that have kind of millions of clauses that with variable elimination can be solved, but the proofs are big because if you have variable elimination, it's just a single resolution step, but then all the resolvents you add, and then you remove all the original ones, and so frequently what you can have is that you add 1,000, remove 1,001, and then just to have one single step. And if the loop is kind of slow, but I guess it can be fixed. So with the current 3 IDs that I showed, it's already kind of a factor 20 faster than the original kind of the procedure that was proposed before. But I guess that this line can go further down.
So would you then add a different modality in a different proof step to avoid the...
No, I think that there should be just a more sophisticated unit propagation routine. You should somehow be able to easily detect that there is a clause falsified. Because what you have when you do this variable elimination, you assign everything to false, and there is then, if you assign one variable more, because everything is using resolution, so if you find one of the variables for which the resolution is done, you have to assign one more variable, and then another clause is falsified. So unit propagation is just with adding a single unit propagation step. There is some clause falsified, but maybe changing data structures, sorting things, you can immediately find it. But now sometimes instead of assigning a single variable, you assign 100,000 of them before actually finding it, which is so there's a lot of I think there's something to gain there. Exactly how to do it is I'm not sure, but I guess with making the unit propagation better would fix this. And already you see with the core first that you can gain a lot. I think there are other things, and the interesting thing is that if you, for instance, would implement this core first implementation as I have it now in a SAT solver, it would be kind of twice as slow. So it's really the checking, how to do efficiently checking in a checker is completely different way of thinking of than doing things in a solver. Because in a checker, you know that as soon as there's no conflict, the proof fails. So you really know, okay, at some point there must be a falsified clause. While in SAT solving, you expect that unit propagation will return a fixed point where there's no conflict in most of the cases.
Actually, what the graph doesn't show is that the different proofs that your procedure can find. Debug trim will find maybe your prune learn clauses. In your example,
Yeah.
pruned, was it a C?
Yeah, no, so
Yeah,
this is not the only slide with results.
Oh.
So let me directly continue. So this is also one of the slides. So this is, for instance, the original formula. This is number of clauses, and so this is on all the benchmarks that they could both solve, glucose and picosat, to have a comparison. Although, as you can see, the running times were much different. Again, so pico, this is the number. So you can see that the size reduction after a single. So you solve the benchmark, check it. There's a big difference between the original size of the formula and the size that is given in after one step. And you can, for instance, in tools that produce the minimal satisfiable course, they iterate this procedure. So this is the picosat proof, so which is then done in memory, which uses kind of the data that's all available within the solver at the point of constructing it. And so if you do glucose with the backwards checking, but without the core first, then the size of the proof is as in the red line, and the green line is what you get when you apply the core first. So kind of to show you that the proofs get smaller when you use this core, so you use this alternative unit propagation. Is this plot clear? So for tools that want to have minimal unsatisfiable course, you really kind of want to take this step, because especially the first steps is very easy, but getting proofs really smaller from kind of after finding a single proof can get much harder. So this can be a big step in actually computing minimal unsatisfiable course, because there's at some point you really will delete clauses one by one with a single sat check. Yeah, so I was happy that I was able to push this, although there was some resistance. That there was at the SAT competition 2013, the organization demanded that, or required that unsatisfiability tracks, that solvers that participate in the unsatisfiability tracks had some proofs emitted. And there were two kind of options. Either trace check, which is the most widely used resolution format, and this delete reverse unit propagation. So we have these clauses with deletion information. And so the competition allowed for 5,000 seconds for each of the benchmarks to solve, and allowed the checker to have 20,000 seconds. And so there were three categories, but for the application category, there were 9 solvers with emitting drep and 2 emitting rep, so ignoring the deletion information. And there were 9 solvers in the hard combinatorial. And the nice thing was that of the top tier solvers like glucose, Ling-a-Ling, they all submitted proof version to the competition. And so some statistics. So of the top tier, so the highest ranked solvers, so they implemented the deletion efficiently. 98% of the DREPS proofs could be checked in the 20,000 second timeout. So practically also 1 or 2 instances of the solvers we could not check because of it reached the timeout, but so practically all the proofs have been checked or refuted by the checker within the time limit. And if you look at so there's some solvers that only used rep, so they didn't use the deletion information. And only kind of 40% of the proofs could be checked. So by having this deletion information, and even with core first and everything else and backwards, which was done here, don't having the deletion information kind of brings down checking 98% of the proofs to checking only 40% of the proofs in the time limit.
Did any of the solvers report an incorrect result, or the proof didn't check?
Yeah. So there are kind of two issues here. There were a few proofs that and even the winners. I think therefore for each solver there was at least one benchmark. Maybe I don't think that mini. So it was one Minisat was the only one I think that had proofs that all went through the checker, and the other ones had maybe one or so that the checker said they couldn't reconstruct it. But that doesn't mean that there might be some ordering difference, especially so if sometimes you delete a clause earlier than you kind of are allowed to delete it, and then the proof might fail. So that there's an implementation issue. It doesn't mean that there's a bug in the solver if the proof fails. But for I think for the winner and the number two in the competition, they all had at least one benchmark where it said the checker said I'm not able to check it. Of course, it could also not be the checker, but let's.
Was there a penalty?
No, there was no penalty. So that's one of the rules was that if the checker says I'm not able to verify it, then the benchmark is just it's the same as not solving it. And that's also the reason it was the first year to let people because it would be in this case if there was only one solver that all the checks go through, that would mean that that solver would automatically be the winner. Yeah, so it's I think it's a tough penalty, because if you say there's a solution and you give the wrong solution, you're disqualified in the competition. But for UNSAT, it's still too early to kind of have this kind of tough rules. Oh yeah, and the other thing is that what?
You want to give the drug out for free first.
Something like that. So what I also discussed it with Leo just before, that there were 30 instances in the competition for which, so there was also on all benchmarks. There were tracks that solvers were run on all benchmarks, and there was no certification for those benchmarks. And there were 30 instances where the fastest solver in that track was at least 10 times faster than the fastest solver in the certified track, which you think, okay, what's going on here? And for 21 instances, I was able to detect that the winning solver had actually a bug on those instances. And the easiest way to check it is, which frequently helps, is you remove the top 10% of the lines, except for the first line, you remove the top 10% of the lines, and then you give it to the solvers again, and then frequently the fastest one is still unsatisfiable, and there's another solver that says it's satisfiable. And
you had some example where there was a zero missing, or there was a line with a zero.
Yeah. So that was one of the. So there was also one of the bugs was where I solved that there was if there's one empty line in the proof format, or in the input file, then it considered an empty clause and immediately said unsatisfiable, but an empty line is just to be ignored. And therefore, by just removing kind of some clauses, and if still the empty line is still in the file, then you will, as long as the empty line is there, it will say unsatisfiable. But other solvers at some point will find a solution because of the missing clauses. Yeah. So there are also things with. Okay. I don't want to probably don't go too much into detail there, but it kind of shows that if there are solvers that they say that sometimes they said they had to turn off some features because it was not easy to implement them using the DREP information, but maybe it was because they're buggy and then it's hard to implement it because you can never. The checker would always would say it's incorrect, but So there were yeah, I'm kind of really in favor of checking things because you can really you kind of see that there are bugs, and solvers actually come up much higher in the rankings because of these bugs, because these faster instances they were not buggy. They were not found buggy in this track, so they were just everything was correct. I only after the competition I used this trick to remove these clauses, and then you see that they are buggy, but it's in the if you look at the competition results, everything is fine.
Does that competition have unknown benchmarks, or are they all known?
There are unknown benchmarks in all categories, and especially in the random category, we generate everything at the phase transition so half of them are kind of expected to be SAT, half of them are expected to be UNSAT, but it's no way you can ever prove UNSAT on these benchmarks. So if you prove that 50% is SAT, then you kind of might assume that the other, but you never know for sure. So in the random category, there is lots of unknowns.
But if you train your solver on known benchmarks, you might not, and most of the benchmarks are known, then there's some chance that...
What do you mean if known? If you say known, it's I thought for known, said known SAT or known UNSAT, but...
Published benchmarks.
Oh, no.
Okay, suppose you train your solver on a set of benchmarks, and it has this U-line bug or something else.
Okay, yeah, no.
You're not going to detect it by rerunning it in a competition.
Yeah, okay, sorry, I had the wrong impression of you. So I thought your question, so in SAT, if it's known, unknown, it means that it's not known whether it's SAT or UNSAT.
The status, yeah.
But so for the competition, we did it 50-50. So 50% of the clauses were somewhere published on the internet, and 50% were contributions, new contributions to the competition. And that's kind of the best we can do, because there's a certain amount of, there's limited number of people submitting, and so some people submit, I think we have one participant that had over 1,000 instances, but if you would select many of them, then you would really favor that one because he also submitted a solver. Then, you kind of win by submitting your own benchmarks and your solver, which is optimized for your own benchmarks, and nobody else knows they're there. So you're really limited in how many new benchmarks you also can use. So it's kind of a 50-50, which I think is a good compromise. Little graph about the competition. So I already talked about the two different tracks. Their solver, the same color means that they're the same solver, but they're in different, either they are in the category where there's no checking and logging, and the other category there is checking and logging. And what you see for glucose and for RIS, their performance is pretty much the same in both tracks. So all features enabled and no logging or no checks. And but if you look for Lingeling, which did not have the deletion information, you really see that if you don't have the deletion information, kind of hardly anything can be checked anymore, and it all breaks down.
So it was 40 lines to add to glucose, and
Lingeling is much more than 40 lines, because Armin uses so many techniques and so many data structures, and he did not implement it yet. I tried to convince him to implement it for the next one. But it's another animal. It's a huge solver with lots of things. But but you can really see that if everything could have been implemented, he would have definitely won also the certified track, if able. But you can see that now glucose won that track. Was the fastest one application, certified application.
Of course, it's like a small addition
To mini-sats, yeah. What do you want to say with that?
Oh, you get lots of bang for the buck for a small addition. So the difference is that you can solve 10 more benchmarks.
Yeah. You mean that's not too much if you consider how many lines of code is added?
Yeah, I was like wondering how many lines of code you need to.
Yeah, so I think that probably Lingerling is about probably 15,000 lines of code, and glucose is maybe 1,000. So, yeah, the difference between. But yeah, so for the SAT competition, this is considered a big difference.
Another thing, the glucose is much faster for easy instances, right?
Yeah. But that's because lots of pre-processing is done, and also what I talked about you before, lots of benchmarks that are submitted are really having bad encoding, and Lingerling in the early stages kind of tries to fix that. And for easy benchmarks, or it doesn't pay off, but for the harder ones it pays off. So at some point, it really Lingerling takes over because then all this stuff is useful. But as you can see, for hard combinatorial software problems, which are typically very small, and yeah, there's not too much encoding optimizations possible, you kind of see that glucose is it's faster, and RIS is also the same story about. There's also just a few more lines on mini-sat. It's kind of similar in size, similar kind of architecture. Yeah, so it's 10 to 12. I have also quite some slides about expressive proofs, but shall I continue with this and
Yeah, I'll have to run. I'll have to leave at 12, but I can stay until 1.
yeah, so but
For me, you should continue.
yeah, okay, so yeah, I don't know, is there somebody else coming in the room at 12 or?
I doubt,
No, not until 1:30, but we might want to have lunch.
Okay, yeah, we might. So, so far I've been talking about rep and derep, and so it covers resolution, this most important learning paradigm, CDCL learning, unit propagation, subsumption, everything is covered in this derep format. But there are some techniques used in solvers, for instance in Lingerling, where all these techniques over here are not covered. And there's another polynomial time checking procedure, which is called RED, which I will explain a bit later, which kind of covers this. So instead of doing this derep check, if you do the RED check, you kind of cover everything which is kind of used in state-of-the-art SAT solvers. What do you mean you add block? There in Lingerling you can add block clauses, yeah. It was, by the way, this was one of the things that was buggy and what was actually motivated the in processing rules and actually the RED, because I just told Leonardo I could make up a small example where, although there was on say a few million of instances, that there was no bug shown in it, and the small example of only 7 clauses was buggy in Lingerling. And it's really tricky to see how to implement it in such a way that it's sound. What were you wondering about block clause addition?
I just thought that one deleted them, but yeah, I don't know.
Yeah, so I think, although we should have, but the nice thing what you can, for block clause addition is what you, so block clause elimination can frequently shrink the instance, and then you can empower variable elimination because there are fewer clauses. But sometimes it's useful to add block clauses for the remaining variables. So you add propagations for the remaining variables.
Oh, okay. I see.
So you first bring it down, and then you bring back to life or new ones for the for things that are still remaining in the formula to have new propagation steps.
So can you remind me what rats? So dework was the deletion.
Yeah, I will talk about the red later. How it's done.
Oh, rat is the Kate.
Yeah, red
Okay,
is the case.
I see.
So, one of the problems that is for which typical SAT solvers are, like glucose, are extremely slow on are the pigeonhole problems, and it's a very easy problem from a high level is that given n-1 holes and n pigeons, could we put the pigeons in the holes such that there are no two pigeons in one hole? And even a little kid can say, okay, that's not possible. But for SAT solvers, if you encode it, it can be proofs can be exponential or will be exponential if you don't use special techniques like the one I in the other in the bigger circle. And one way to do it is you can do it with extended resolution, which kind of has, I think, a cubic size in the number of pigeons. And it's kind of, you translate the problem from n-1, n pigeons in n-1 holes to n-1 pigeons in n-2. And you do that n-1 times, and then the problem becomes trivial. But this is, you cannot, so the proofs that you can do over here, if you express those proofs, then DRUP says, I cannot explain this. Another technique, which actually is pretty useful for some benchmarks, is called bounded variable addition. And given a CNF, we try to find a set of clauses which we can replace by a smaller set of clauses. By introducing a new Boolean variable x, for instance, and x does not occur in the formula. So the smallest example for which this works is we have these clauses, and we want to replace them by these lemmas. Now, if we add a single one of them to the formula, if you assign this to false, and x does not occur elsewhere, then you can see them, there's no conflict. Yeah? So how do you deal with such a technique? And even if you have extended resolution, which is which you might think, okay, because of the pigeonholes, you have small extended resolution proofs, but even for this kind of techniques, it's not easy to make an extended resolution proof which can express this. What?
I mean, this is the case where it's not logically equivalent but equisatisfiable.
Yeah. Although it's no, well, yeah. So in this case, even it's somewhere in between. Because with block clause addition, you really can throw out solutions. So if you do this trick, the number of solutions stays the same. And so the both formulas have the same set of solutions over the common variables. So it's a kind of in between satisfiability equivalent and logical equivalent.
You can put it existentially. Say it's equivalent to exists X,
Yeah.
right?
Yeah. Yeah.
It's logical equivalence if you put it existential.
Yeah, so I was under the impression that you would always preserve equivalence under existential closure. But what you say now is that blocked clause addition.
That's not. Can I give you just a simple example? So we have A or B, and we have not A or not B. So if, say, this is the formula, we can add this clause, which is blocked with respect to this formula. So if we add it, then so block clause addition allows you to add this clause, which clearly removes one of the solutions. So there are different techniques, but so in potentially this kind of there are techniques that so an extended resolution in general has this property that it's kind of in between. So it has the same set of solutions over common variables. Yeah. But to express this is much you cannot really so you can do it, but it's tricky. And you actually want to have a technique. So the red I will explain on the next slide is something that you can. All these clauses have red, and that is kind of. So you don't have to make lots of extended resolution steps to explain why you can add it. You can just do exactly what the solvers are doing now. If you add a clause to the database, just say you add it, and if you delete it, you say you delete it, without having a whole set of additions and a whole set of deletions in order to convince the checker that it's actually sound. Oh, yeah, first this slide. Yeah, so this is kind of a motivation why you want to use this bounded variable addition. So these are free pigeonhole problems. These are free bioinformatics problems. If you run glucose without BVA preprocessing, it's these are the running times. If you do first BVA preprocessing, these are the running times, and you see that there's a large speedup. So for certain problems, you really like to have this kind of preprocessing step because it's it can give you a lot of runtime. Yeah, you want to ask something? Oh. This we've seen. This is the rep procedure, and now the red procedure. Yeah, I thought so. There's a large example on the next slide, but a lemma has red or resolution asymmetric tautology if it has rep, or if there is a literal in the lemma such that all resolvents on L on the literal, namely with all clauses containing the complement of the literal, are either tautologies or they have rep. So you have a clause and a certain literal. It must be that if you take all possible resolvents on that literal, so if there are, say, 10 clauses containing not L, then you have 10 resolvents, and all these resolvents must either be tautologies or they must have rep. That's the property. Shall I go to the example?
Yeah.
So we have a formula. So this is kind of the smallest formula for which a red proof is smaller than a rep proof, although they can be exponentially smaller. But so you need some clauses in order kind of to show off. So this is 8 clauses, unsatisfiable, and this is a red proof. And the triangle means that the clause has red and no rep. So, and it's easy to see that this clause has no rep because all clauses have length 3. If we assign not A to false, which means we assign, so we assign A to false, or not A to false, which means we assign A to true, then some literals gets falsified, but since every clause is length 3, there will be no unit propagation. Yeah, so it's easy, clearly, does everybody see that there's no, that rep is not going to work? And it's not, no. So we're now going to check it, so do forward checking. And now we just detected, okay, it has no rep. So now we're going to check if it has ret. So what are we going to do? We're going to do all resolutions with clauses containing the complement of this is A. So we take all clauses, so this clause contains A, we do resolution, and that brings us clause B or C. We do the same here. We have the clause C or D after resolution, and we have the clause not B or not E. Yeah, because resolution gives us these three clauses. And it has ret if and only if all these are rep. Yeah, so that's the definition.
Because none of them are tautologies.
Because none of them are tautologies, exactly. So if there's a tautology, we can get rid of it, and then we have to check for all of them whether it has rep. Yeah. So first we create those three using the resolution. So we take this clause, we compute all the resolvents. That's the first step. And now we're going to check, and we see, okay, we can reconstruct it using rep. Like we did before, we can do the same thing with C, D, and we can do the same thing with not B or not D. And now we checked it. Now we checked it all, and now we know it is ret, and we can add it to the formula, and we remove all the resolvents. And now we can use this clause as a antecedent for B, and then we check the empty clause, and we are done. So what you can see here is that we have only three clauses for the proof.
So you have an example with where x was introduced as an extra variable, and the intuition then is that you select x and resolve on that, and the resolvents will be rho.
Yeah. So what you have is that, so for instance, we first add all these three with x, and then we check for all resolvents on x, whether they are tautologies or have rep. But since not x is not there yet, everything has, all resolvents have ret or rep because there are 0 resolvents. So first we can add these for free, because these are not in yet, because x is new. And then we, for instance, we add this clause. Then we do all resolutions, and then we end up with these three clauses, which have rep, because they are exactly, and we do the same thing here. We do add all resolvents, that brings us these clauses, and there. So it's clearly to see why it works for this technique. But the nice thing is that it works for all known cell techniques. So it's I think, a very elegant way of checking things. And the same thing for extended resolution proofs. For extended resolution, so everything is tautologies. So, for instance, we have the variable x or so, which means that x is equivalent to. So we add a new variable x, which is the end of A and B. So we can do the first trick here. We add the x because there's nothing there. And now if we do resolution on these two, we get a tautology. And now we do a resolution on these two, and we get a tautology. So for extended resolution, red works because of tautologies. For this technique, it works because of rep, and there are techniques where you have the mixture. Yeah.
But your definition is on the previous slide is.
Yeah, no, the definition. No, so sorry. The definition is kind of. I want to keep it short, and I hacked it in last night. So.
No, yeah, it's good. But what strikes me is that lemmas are not recursively red. There's no recursion in that.
No, there's no recursion. We have been thinking about it, but there's no techniques which requires recursion. Because everything becomes, then if it fails, then the clause there must be a literal, and also in the proof format we explicitly demand that the first it has to have red on the first literal. So if you add a clause in the proof, then it has to have red, so that to really reduce the checking cost. Because then the solver has to know on which literal it is, which of course for this kind of examples it's easy. Yeah, but I wanted to have the definition, but there's in the papers there's much more formal, especially Matti likes to have much more formal. But this is kind of, I thought here.
Is it sound to have recursive red, or is it?
I think it sounds.
Yeah.
But yeah, I have to. Yeah, so it's not obvious, I think. And so, but if you, for instance, have a formula, so with n variables, and all clauses have length n, and you have all 2 to the power n clauses, then any resolution proof will be exponential. But the red proof, you you add all the unit clauses. So you say or say you have x1, x2 to xn, and that's the proof. And then you end with the empty clause. So for these kind of formulas, just to give you an example, where you have just only the units and you're done.
That was the example of the next slide with ABC.
No, yeah, but this is 4 literals. This is not 3 literals.
Oh, okay.
But it is kind of similar, yeah. So, but you can generalize it as if all clauses have the length of the number of variables, then you can just add all the clauses have red. So, but there's also all kind of nice things that you have small proofs for small red proofs. So I think it's really nice that you compute first all these resolvents, like you compute all these edges, but then you can discard everything and you have this compact information. Yeah. So this was kind of the toolchain we had. So we have this sequence of added and deleted red clauses, and then we give it to the checker. But now the question is, do we trust the checker? Because things have become much more complicated, especially if you want to have all the optimizations in the checker. So it's now about 400 lines of code, the checker. But yeah, can we, so are we done? So no, I think it's really good to have a verified checker. And so one of the focus of future work will be to kind of use this tool that we have now, which also for red, it gives this reduced course, reduced proofs, optimal clause deletion information. So we come here, we can get this big proof, we've added, deleted, and clauses red lemmas. We give it to the kind of the proof trimmer, which is actually the same as the checker before. So this is the same tool. This is this drep trim tool we have now, which significantly shrinks it, optimizes clause deletion information, and then the proof is small enough that we can do it with a verified checker. So then lots of optimizations can go, and we can then check it with something which we trust even more. And so this can if, for instance, see this, you can implement this in say 100 lines of code. So, but this is one of the things I think is very nice to get it done. And Nathan, which I showed you as a co-author of this work, is doing its PhD on this.
Actually, I was looking him up on the web today for a different reason, but it seemed that he had a defense last week.
Yes, yeah, his proposal.
Oh, proposal, okay. I didn't read it.
Yeah. No, what he
Because
is.
it said something about verified proof checkers.
Yeah. No. So he's working on a verified, mechanically verified checker that can have added and deleted red clauses. And he makes it in ACL2 and. Yeah, and the nice thing about ACL2 is that you can get to say 60 or 70% of the speed of C. If you, yeah. But there's lots. So you have this stop chase. I don't know if you're familiar with, but there are all kind of low-level techniques which are now supported. But of course it makes the proof much harder. So he has on a high level he has a proof. And now we have a low-level implementation, and it's bringing them together. So that's, but it's probably a year work of having it all together. Because these proofs can take a long time. Just to give you a little bit an impression about this proof reduction, which we have now, although I think the more important thing is almost this, that you can optimize this deletion information, which can really helps to guide the unit propagation, because when you first get it, everything is not so clear. This is so the size of the input proof of glucose, and this is the size of what the proof gives. But so you can see it's slightly more than a factor 2 that you can reduce it, the proof, but by optimizing this deletion information, it's yeah, and also the clauses, the original clauses is kind of, that is even, yeah, that was the plot I showed earlier. You can have easily a 90% reduction in the original clauses. So you have a much smaller number of original clauses, and you have a smaller proof and optimal deletion information, which makes it possible that even a mechanically verified checker should be able to deal with this in a reasonable amount of time. So, yeah, so the kind of the contribution slide again, and yeah, what is actually should.
So the rat proofs is forward. It's not backwards. Right?
You can do it both. But so so the checker, the verified wait. So yeah, the checker as things would look here will go forward. Because if you have optimal clause deletion information, it's really, there's no use of going backwards. That doesn't make sense, because everything will be in the core. So you don't gain much by going backwards, and the cost of going backwards is that you have conflict analysis and all this. It's things you really don't want to verify. So you really want to have things as clean as possible. So the verifier will go forward with all the optimal clause deletion and the smaller proof and the smaller clauses. But you can do the C version, the trimmer, the proof trimmer will go backwards also for the red. You can also do the same trick here if you do backwards. It doesn't. There's no. You see that there's not much difference if you go forward or backward regarding the red. You just, when you check it, you take all the resolvents with everything above in the proof. So you just don't do resolution with anything that is over here. You just do resolution with everything that's over there.
that works both forward and backwards.
Yeah.
What you presented here was a forward version,
Yeah, to keep it more clear, yeah.
and your trimmer goes backward.
Yeah, so the trimmer goes backward. Trimmer, so the one that I have in mind, which is also, we're kind of, let me, so the one I have in mind, which I hope to finish maybe in a month or so, it also has this bar up. So it combines this and this, which requires going backwards and using deletion information.
I was asked to shut up so you can finish.
Yeah, no. So I'm, as you can see, I'm practically finished. So the work over here does look forward red, and also, but there's no, so by combining this deletion information and the procedures I have here, I think you can have everything. And then combining that with checking the reduced output to a verified checker, I think then you have all possible things you kind of want for checking. Yeah, so this kind of sums it up. So here, I think this is maybe the more important point for discussion later. Should this kind of proof logging be mandatory for competitions? Maybe also the SMT competition. I noticed that at least I used this line at the FMCAT, and the only people that discussed these things with me during the coffee break were saying, "Please do not do it. This is too hard, and no, really kind of should back off." So in the SAT community, people are more positive about it, but in the hardware model competition, they really fear that it might be extremely hard combining BDDs and all kind of stuff into this. But I think it would be good to have more faith in it because the tools definitely here have lots of bugs as well. So yeah, that's it. So there are I have 4 publications this year on this proof checking, and yeah, so I have some more plans, so there will be follow a bit more. Yeah, thanks for the attention.